This is my understanding of how the PC boots, and also how it works. If it's helpful or if I got anything wrong, either way please drop a comment. It's mostly about the x86 architecture, Intel, BIOS, MBR, Windows operating system etc. In addition to the most central steps of the boot process, I have included a few more details. But if the extra information is a little overwhelming, continue watching anyway and the summary in the end will make things clear. How does a computer boot? Short answer. When you press the power button, the BIOS tests all the essential hardware in the PC and also performs a check on itself. And then depending on the configured preference of boot devices, it will locate the operating system and load it. So now let's have a more detailed look at it. To understand the process better, we'll take a quick look at the main components inside a PC. The most important part is the processor, which executes programs. Then you have the chipset, which used to almost always come as a set of two chips called North Bridge and South Bridge. The North Bridge connects the CPU to the high-speed components like the system memory, AGP graphics slot and the high-speed PCIe slots. The South Bridge connects all the slower devices to the CPU through the North Bridge. Let's identify the North Bridge and South Bridge on some motherboards. On some motherboards you might see two BIOS chips, main BIOS and backup BIOS. The backup is used to restore the BIOS code on the main chip to the factory default version if it gets corrupt, but if the chip hardware itself is damaged, then the backup chip will take over as the main BIOS. Back to the chipset. With some updates to the chipset later on, the North Bridge was renamed the MCH and the South Bridge was renamed the ICH. With some more advances in technology, later on, almost all of the features of the MCH were incorporated into the CPU itself, and the ICH with some changes was replaced by the PCH. With this basic knowledge about the hardware, let's look at the boot process. On being asked how does a computer work, you would say, a computer works by running programs or executing instructions. That's absolutely right. And to be a little more technical, it's the microprocessor on the motherboard that runs the instructions which are in the memory. But when the computer is just turned on, the CPU registers and the main memory are empty or contain random data. So how does the processor know what program to run and where to find it? The solution to this problem is to have the microprocessor programmed when it's manufactured to start executing instructions from a fixed address every time the computer is turned on. So let's press the power button and see how it works. On pressing the power on button, a high signal or digital 1 is sent to the reset pin on the processor and kept high for at least a few clock cycles, at least 4 clock cycles for the 8086 processor. The minimum number of clock cycles differs for different processors. The 8086 receives clock signals from the 8284 clock generator, which is a chip installed on the motherboard. It is this chip that provides the reset signal to the processor. When this reset signal goes from high to low, the CPU is reset, meaning the CPU registers are set to predetermined states or known states. The 8086 CPU registers are set to the following values. It takes about 10 clock cycles to reset the 8086 CPU registers. The number of registers varies from processor to processor, so each processor will need different number of clock cycles. Registers are in a way similar to RAM. They are used to store data temporarily, but extremely small in capacity but extremely fast compared to RAM. You can pause and read here if you'd like. Before we move forward, let's check out one more definition of how does a computer work. An extremely simplified way of explaining how a computer works is, it fetches the next instruction, decodes it and executes it. That's how the computer works from the moment you press the power button till you click on shutdown. But how does it start? What or where is the starting point? Where is the first instruction? That is what the reset vector is defined for. Vector means address. After resetting the registers, the CPU generates the reset vector using those register values. How does the 8086 processor generate the reset vector? The value of the code segment register is FFFFH and the IP register is 0000H after a reset. The CS is left shifted by 4 bits to get FFFF0H, in effect just multiplying it by 10, and is added to the instruction pointer register value to get the 20-bit physical address FFFF0H. The reset address or reset vector is the address where the CPU picks up the first instruction to execute after it's powered on. Since the registers are always set to the same values every time the computer is turned on, so the reset vector calculation always results in the same value. The reset vector for the 8086 processor is at FFFF0H. Last 16 bytes below 1 megabyte. The reset vector for the 8286 processor is FFFFF0H. Last 16 bytes below 16 megabytes. The reset vector for the 8386 and others is FFFFFF0H. Last 16 bytes below 4 gigabytes. The BIOS ROM is mapped into this address, reset vector. To say it in another way, this address points to the BIOS. The first few instructions at FFFF0H on the BIOS are executed from the BIOS itself. This method of executing instructions from another location directly without bringing them into the RAM is called execute in place. A common place you might find the XIP implemented is during the 0 or first stage bootloader execution. This first instruction at this location just contains a jump instruction to the start or actual beginning of the BIOS. The BIOS is also called System BIOS, ROM BIOS, PC BIOS, BIOS ROM, Motherboard BIOS. The BIOS is a collection of programs stored on a chip. It is a flash memory chip or EEPROM chip on the motherboard that contains a set of programs that perform the most low-level operations. The BIOS chip is usually connected to the south bridge of the chipset. The physical interface between the BIOS and the chipset is usually a relatively low bandwidth bus. For many years, it was the LPC or FWH bus. Intel later began using SPI for the BIOS interface on their newer chipsets. The BIOS mainly consists of these 3 parts: startup routines, service handling routines, and hardware interrupt handling routines. Startup routines comprise of the post and boot routines. The post and boot routines are used only during the startup process. The service handling and hardware handling routines remain in the memory till the computer is shut down, but only when operating systems like DOS were used, not Windows. The service handling and hardware routines are used by older operating systems like DOS to perform I/O activities like display a character on the screen, accept keyboard input, read-write to storage devices, etc. When an operating system like Windows is installed, the BIOS service routines are used only during the initial startup and boot phase. The first set of routines or programs the BIOS runs is the post. The power on self-test is a set of routines in the BIOS ROM that checks the BIOS itself and all the hardware components of a computer. The list of devices and the particular order in which it checks them depends on the firmware, etc. But most firmware would include at least the minimum hardware required to start up and operate the PC. On most BIOS, the tests performed and their order would be roughly like: the CPU registers are checked first by loading some values into all the registers and reading them back. Then the BIOS routines are checked by performing a checksum on the BIOS itself. Then the keyboard, etc. And they are also initialized. The tests it performs are not a thorough or advanced diagnostics check of the devices. So even if the devices pass the test, there still might be some issues with the devices. Errors encountered during the post are indicated with a combination of long and or short beeps. Before the video adapter is initialized, error messages are communicated only with beeps on a blank screen. But more informative messages are displayed on the screen with or without beeps after the video adapter is initialized, like so. The post also sends hexadecimal codes to the I/O port address 80 for every single test it does. Every post routine that is executed. So if you need to troubleshoot or want to have a closer look at each post test that runs, you can insert a special card, called the post card or post diagnostic card in a bus slot on the motherboard to look at each test performed. After testing and initializing the RAM, the BIOS copies itself into RAM if shadowing is supported and enabled. The BIOS is copied into RAM but in the same address range previously occupied by the BIOS ROM, thus disabling the BIOS ROM in the process. From here on, the BIOS runs from RAM and not from the ROM chip. Because 32-bit and 64-bit operating systems nowadays use their own device drivers etc. and not the BIOS service routine, so it does not make any sense shadowing the system BIOS. One of the major functions of the BIOS is to provide the interrupt service routines. They are the same service handling routines and the hardware interrupt handling routines. When a program or hardware device needs the CPU to perform any basic task, like print something on the screen, read or write to the hard disk etc., they send a signal or command to the CPU, which is called the interrupt signal or interrupt command. For example, when a program needs the CPU to print a character on the screen, it issues the INT command with the number 10. When the CPU receives this interrupt command, it stops whatever it's doing and begins executing a small program called the interrupt routine or interrupt handler. This interrupt routine, also called interrupt handler, contains instructions that tell the CPU exactly how to perform a specific task, like print to screen, read or write to a hard disk or accept keyboard input etc. The starting addresses of these interrupt routines are called interrupt vectors and are stored in memory in a table called the interrupt vector table. The BIOS sets up the interrupt vector table at memory address 0h in RAM, at the start of memory. The vector table may contain up to 256 interrupt vectors and each vector takes up 4 bytes. So the memory addresses 0h through 3FFH are reserved for this table. So it takes up the first 1 kilobyte of memory. Interrupt vectors are stored in segment offset format. The first 2 bytes contain the IP register address and the next 2 bytes contain the CS register address. The 2 addresses together provide the 20-bit address of the interrupt service routine. Each interrupt vector also has an interrupt number associated with it. This interrupt number is used to call the ISR by invoking the INT instruction. Example: the INT19H vector resides at interrupt vector table address 64H. The BIOS initializes INT19H to address FE6F2H on startup. The BIOS uses the memory area in RAM from 400H to 4FFH to store data that it uses while executing the device service routines and also to store data that it generates from the execution of post. For example, it stores the list of equipment it finds while running the post. It stores the list at memory location 410H. To access this list of equipment, the instruction int11h is invoked. The interrupt 11 is associated with the vector F000F84DH at memory location 44H in RAM. This segment offset address is used to calculate the 20-bit physical or absolute address, which is the starting point of the equipment list service routine. Towards the end of post, it will also look for any expansion ROMs or device BIOS to initialize any peripheral devices. This device BIOS is on a chip located on that particular peripheral device itself or on an expansion card on the motherboard. The chip contains service routines to support features of that device. It searches for video expansion ROMs at addresses ranging from C0000H to C7FFFH in 2K increments, and other expansion ROMs at addresses C8000H to DFFFFH in 2K increments. After it finds the expansion ROM, it executes it by performing the following steps: copies the appropriate image from the ROM into RAM, disables the expansion ROM's address decoder so that the code runs from RAM and not expansion ROM, executes the initialization code, write protects this memory area. When the BIOS has completed performing the post routines, it will produce a single beep sound indicating all the devices are fine. If there's a problem with any device, the BIOS indicates it with a short or long beep, or a combination of short and long beeps. or it may also not produce any beep. BIOS also compares the data about the actual hardware found during the post-process with the system configuration data stored on the CMOS chip. If they don't match, the BIOS prompts you to change the settings if you want. Up to this point, all the actions performed are considered to be part of the startup process. Following actions are considered part of the boot process. After the BIOS is done processing all its tests and initializations, the last thing it does is invoke the interrupt19 service routine. The int19 vector resides at memory location 64H. The segment offset at this location is picked up and the physical address is calculated. This address points to the start of the bootstrap loader routine in RAM, which is somewhere here, and passes control to it. There are two types of boot actions: a warm boot and a cold boot. A warm boot is performed when you click on Start and then Restart, or press the Ctrl-Alt-Delete keys and restart the system. A cold boot is performed when you press the power button. What tests are performed or not performed during a soft boot depends on the version of the BIOS, manufacturer, etc. During a warm boot, the memory above 64 kilobytes is usually not tested. The BIOS checks to see if this is a warm or cold boot by checking the value at memory address 472H. A value of 1234H indicates a warm boot. Anything else is considered a cold boot. This area is referred to as the BIOS data area, as we have seen briefly earlier. The BIOS uses it to store data temporarily. It also copies a lot of information from the CMOS RAM into this area, which it uses during the post and at later stages too. Within the CMOS RAM chip is a byte of data called the shutdown status byte. A value 00H in this shutdown byte indicates a hard reset. If it's a hard reset, the post performs all tests and initializations. When the PC is turned on, this shutdown byte along with a lot of other information from the CMOS RAM is loaded by the BIOS into this area. So when the int19 bootstrap loader service is called, it will read the first 512 bytes, called the MBR, from the boot device. That is the hard disk drive. Assuming the hard disk drive is set as the first boot option in the boot sequence. This boot sequence information, the system time, information about the hardware on the computer and much more, is stored on a CMOS chip on the motherboard. This CMOS chip is a RAM chip, so it needs a battery to retain its data. So after reading the first 512 bytes, it checks the last 2 bytes. If the last 2 bytes is not AA55H, then the BIOS will not consider it as a valid MBR and it will continue to check the next boot device. If it does not find a valid boot record on any of the boot devices, then it will call the INT18H, which displays a message like "No boot device found." Press F1 to continue. If it does find a valid boot record, then it loads the MBR at the address 7C00H in RAM. A very important requirement the BIOS places on the partitioning format of the primary disk is that the very first sector of the disk should be the master boot record. To say it in another way, for the BIOS to load the MBR should be the first sector on the disk. The MBR contains information on how all the partitions on the disk are organized. And there is only one copy of the MBR on the disk. There is no backup copy. If the MBR gets corrupt, you will not be able to access the disk unless you repair or rebuild the MBR. So how does this MBR load the OS? Let's take a closer look. The master boot record contains the master boot code, the partition table, and the boot signature or end of sector marker. End of sector marker marks the end of the MBR. These 2 bytes are always AA55. The master boot code is 446 bytes long and contains code that checks the partition table to find out which partition is the active one. Active partition is the partition from which it will load the operating system. The master boot code identifies the active partition by looking at the active flag, also called the bootable flag. A value of hexadecimal 80 indicates the partition is the active partition. 0 indicates a non-active partition. Now that it has identified the active partition, it finds out the starting sector of the partition and loads the first 512 bytes of the active partition in RAM. The first sector of the disk is called the master boot record. And the first sector of each partitions is called the partition boot record, partition boot sector, volume boot record, volume boot sector, or sometimes just boot sector. The MBR relocates itself to another location in memory from 7C00 during its execution. So when it loads the volume boot record, it loads it in the same location 7C00 where it was initially loaded by the BIOS. The code in this active partition is also called the second stage bootloader or secondary bootloader. The code in the MBR is called the first stage bootloader or primary bootloader. The startup routines in the BIOS is sometimes referred to as zero-stage bootloader. The main task of the first stage bootloader, other than performing some basic minimum initializations, is to load the second stage bootloader. After the second stage bootloader is loaded into RAM, control is transferred to it. The second stage bootloader then loads the operating system. The partition table is used by the BIOS and the operating system, and has information like the location and size of the partitions on the disk. The partition type value specifies what file system exists in the partition, and the bootable flag indicates whether it's the active partition or not. Coming back to the boot process, the contents of the VBR depends on the operating system and file system. So let's assume the file system is NTFS and the OS is Windows. The version of the Windows also matters, but we are not going to get into the details. The two main functions of the volume boot record is to provide the operating system with information about the structure of the partition, like size of the sector, number of sectors in a cluster, type of the storage media, and much more, which is contained in the BIOS parameter block. And second function is to locate and load the NTLDR in older versions of Windows and boot MGR in newer versions of Windows. That is done by the boot code or bootstrap program. If the boot sector can't find the bootmgr file in the root directory, it displays a message saying bootmgr is missing. The first thing the bootmgr does when it starts executing is to switch the system to protected mode. Then it enables paging. Once protected mode with paging is enabled, Windows is considered fully operational. If there is more than one boot option, bootmgr will provide the user with the options to select from. If there is only one operating system installed, then bootmgr will load the OS by running winload.exe. Winload.exe loads the NTOS kernel.exe and its dependencies. So after a few more programs are run like the NTOS kernel.exe, session manager subsystem, the winlogon.exe with the help of a few other important processes, authenticates the user and loads the user settings, thus completing the entire boot process. The user can now use the computer. When you press the power button, the clock generator sends a high signal to the reset pin on the processor. The signal is kept high for a few clock cycles. When the signal returns to low, the CPU registers are reset. The CPU uses these values to generate the reset vector. The reset vector points to the entry point into the BIOS. So, the CPU starts executing instructions from this location. The first set of instructions are called the post. The post checks all the hardware and initializes them, and also checks the BIOS itself. The tests performed would be roughly like the following. It then sets up the interrupt vector table at the start of RAM. It then searches for any expansion ROMs and initializes them. It finally compares the list of hardware it detected during the post with the list of hardware on the CMOS RAM chip. After the post is complete, the BIOS calls the interrupt 19. The interrupt 19 bootstrap service routine looks up the boot priority sequence listed in the CMOS RAM and tries to locate a valid boot device. A valid boot device is one that has the last 2 bytes of the first sector as AA55. If it does not find a valid boot device, then the interrupt 19 calls the interrupt 18. The interrupt 18 displays a message, "No boot device found." If the interrupt 19 does find a valid boot device, then it loads the first 512 bytes, which is called the master boot record, into RAM at location 7C00. The MBR checks all the partition table entries to locate the primary partition. The MBR relocates itself to some other location in RAM during its execution. So when it finds the primary partition, it then loads the partition boot record at 7C00 and passes control to it. The partition boot record locates and loads the NTLDR in older versions of Windows or the boot MGR in newer versions of Windows. It looks for it in the root directory of the partition. If it does not find the boot MGR file, it displays a message saying, boot MGR is missing. If it finds the boot manager, it loads it in RAM and hands over control to it. The first thing the boot manager does is switch the CPU to protected mode. Then enables paging. If there is more than one boot option, the boot manager will provide the user with options to select from. If there is only one operating system installed, then the boot manager will load the OS by running winload.exe. Winload.exe loads the NTOS kernel and its dependencies. So, after a few more programs are run like the NTOS kernel.exe and the session manager subsystem, the winlogon.exe, with the help of a few other important processes, authenticates the user and loads the user's settings. The boot process is now complete. If you like the content, please comment, like, share and subscribe. Thank you for watching.